Hello and hi everyone. So in this video, we are going to discuss about the confidence intervals and also the sample size estimation. So let's discuss about the confidence intervals first. When you take a sample survey, it is not sufficient to simply report the average height of trees, for example, or you cannot simply report sample proportion of voters who intend to vote for any candidate in a general election. What you need to do is you also need to give an indication of how accurate your estimates are. So in statistics, the confidence intervals are used to indicate the accuracy of an estimate. And if we look at the next slide, we often use 95% confidence intervals. So what is 95% confidence intervals means? It means that if we take samples from our population over and over again and construct a confidence interval using our procedure for each possible sample, we expect that 95% of the resulting intervals to include the true value of the population parameter. It means that if we are going to estimate whether our population total included in the confidence intervals, then this is how you can measure or estimate the population total. And in probability sampling from a finite population, only a finite number of possible samples exist. And we know the probability with which each will be chosen. If we could generate all possible samples from the population, we could also calculate the exact confidence level for a confidence interval procedure. And if you remember in our previous example, if I'm not mistaken, it is from example 2.2. We have come up with 70 possible samples, and we also able to calculate the population total and also the standard deviation of each possible sample. Then in this case, we are able to also calculate the confidence interval for each 70 possible sample, right? So yeah, maybe it is in example 2.1. I do not really remember. You can check again if it is from example 2.1 or example 2.2. We have 8 respondents, for example, and from the 8 respondents, we are going to randomly select only 4 samples, okay, out of 8, which means that we have 70 possible samples. Let me check again. I would like to, yeah, it is 8. All right, it is 8. So our n here is 8 and our sample is 4. Okay, so 8 combination of 4, we come out with 70 possible samples, and we know that the population total for the 8 sample is 40. So our population total is 40. Remember, this is not the estimated population, but this is the population total. Okay, it is not the estimated population total. And you can use this formula to calculate the confidence interval, that is the t hat. T hat here is the estimated population total of each sample. If we have 70 possible samples here, it means that you should be able to calculate the estimated population total for the 70 possible samples, and also the standard deviation of the 70 possible samples, right? And for the lower limit, we will use the hat minus 4 times standard deviation, And for the upper limit, we will use estimated population total, or T hat, plus 4 times standard deviation. All right, and let's look at our sample. Let's look at our first sample. So remember, we have 70 possible samples, and this is our possible sample number 1. Okay, and the respondent selected for possible sample number 1 is respondent number 1, number 2, respondent number 3, and respondent number 4. And the y value for each respondent is 1244. Okay, the respondent number 1 has y value of 1, respondent number 2 has y value of 2, respondent number 3 has y value of 4, and respondent number 4 has y value of 4. Please do not confuse between the sample and also the y value. In calculation, we will use the y value and we will not be using the sample value. Okay, this is actually not a value, it is just an indication of or the ID number of each respondent. Okay, so from here you should you should be able to calculate the variance and also the standard deviation. Okay, and first you must calculate the mean score of the sample number 1. Okay, sample number 1. So use these values. Okay, 1, 2, 4, 4. Okay, so 1 plus 2 plus 4 plus 4 divide by 4, you will get the mean value is equal to 2.75, and from there you can calculate the variance. Okay, you need to have the mean score value here to be able to calculate the variance, and by using the variance formula that we have discussed before, you can calculate the variance value. And in this example, the variance for sample number 1, okay, possible sample number 1 is 2.25. Square root 2.25, you will get the standard deviation of possible sample number 1. You will get the value which equal to 1.5. You can also use this formula, okay, to calculate the variance or also the standard deviation. Now, recall that to calculate the estimated population total, now that you already have the y bar, okay, to calculate the estimated population total for sample number 1 again, okay, you need to use this formula, that is the population size times the y bar of the sample number 1, okay, times the y bar or the mean score of sample number 1. So from here we know that we have 1, 2, 3, 4, 5, 6, 7, 8. So our population size is equal to 8 here, and in previous slide we have calculated the mean score of sample number 1, that is 2.75. And by using this formula, the estimated population total for the possible sample number 1 is 22. Okay, 22. And then from here, since we already have the estimated population total for possible sample number 1, and we have also calculated the standard deviation for possible sample number 1, okay, I think I should write it here. For sample number 1, okay, confidence interval for sample number 1 will be the estimated population total, that is 22 minus 4 times Standard deviation, what is it? Standard deviation is 1.5. That is for the lower limit, and for the upper limit is 22 plus 4 times 1.5. So from here you will get the confidence interval that is equal to 16 and also 28. This is for the sample number 1. And the CI of the selected sample does not include 40. Alright, the confidence interval here does not include 40. And if we calculate the confidence interval of all 70 possible samples, 54 samples will have CI that include 40. Thus, we have 77% chance that the selected sample will include the total population. Okay, now I will show to you about this one in the later slide, but let's look at our another example. This is for possible sample number 1. This is another random sample. Okay, I will put it as sample X here. We don't know which like the number of sample here. So 3, 4, 5, 6, and the value of Y, the value for respondent number 3, the Y value is 4. Respondent number 4, the Y value is 4. Respondent number 5, the Y value is 7. And respondent number 6, the Y value is also 7. Okay, and then again you can calculate the mean score for the sample X here, sample X, and the mean score value for sample X is 5.5. You just use the same formula as the previous example, and again use the formula to calculate the variance. Okay, the variance for possible sample X, and you will get the variance value is equal to 3, and then the standard deviation of the possible samples X is 1.7321. So from there, okay, again you have to calculate the estimated population total for possible sample X, and by using this formula, the population size times the mean score of sample number X, you will get the estimated population total is equal to 44. Okay, and then from there, again by using the same formula, the estimated population total minus 4 times standard deviation for the lower limit, and the estimated population total plus 4 times standard deviation for the upper limit, you will get the confidence interval for possible samples number X is equal to 37.0716 for the lower limit and 50.9284 for the upper limit. From here, we know that if you notice here, the 40, the population total, our true value, our parameter value, included in this confidence interval. It is included, right? So if we calculate again, if we calculate for all 70 possible samples, 54 samples will have confidence interval that include 40. All right, so just to make sure that you are not confused, I've shown earlier that estimated sample, the calculation for CI for sample number 1, and maybe down here we will have sample number X until we have 70 possible samples. So we should be able to calculate the mean score, the standard deviation, the variance, and the confidence interval for each 70 possible samples here. Okay, and if you calculated the mean score, estimated population total, standard deviation, you will notice that this is for the 70 possible samples. Number 1, number 2, number 3, 4, until number 70 here, right? So if you notice here, if it is not included, if the confidence interval here does not include the population or the population total, does not include the population total, we will um, mark it as 0 here. Okay, the same goes to second one, mark it as 0. But for any sample which include 40 as the 40 in the confidence interval, we will mark it as 1. So if you look here, we have few 1 here, okay, and then if we calculate everything here, you will obtain that 54, right? 54 or 55. Let's look at 54. 54 sample will include 40 in its confidence interval. Okay, will include 40. This is number 1, this is number 2, number 3, until number 54. I think it will maybe around here. This is number 54, right? And the rest will not include the population total equal to 40, the one that we mark with the 0 point. All right, and so from this example, we know that each individual confidence interval for possible sample number 1 until possible sample number 70 either does or does not contain the population total of 40, right? So in our example here, 54, only 54 possible samples include the population total of 40 in its confidence interval. Thus, we can say that now 54 out of 70 possible samples, or equal to 0.77, or 77% of all possible samples will include the population total equal to 40 in its confidence interval. So this means that if we take simple random samples of 4 elements without replacement from this population of 8 elements, there is a 77% chance that our sample is one of the good ones whose confidence interval contains the true value of 40. This procedure thus creates a 77% confidence intervals. And of course, in real life, we take only one sample, right? And we do not take all 70 possible samples. Only one possible sample will be randomly chosen from all. And we do not know which one will be, or we do not know if our sample will be one of the good ones. For example, in example 2.7, let's say sample X, which consists of element number 2, 3, 5, 6, that falls into the into a good sample, because the confidence interval include 40, and or sample Y, for example sample number 2, sample which consists of element number 4, 6, 7, 8, which does not include 40 in its confidence interval. We do not know which one will be selected as our sample. So what we can say that the confidence intervals give us only a probabilistic statement of how often we expect to be right. And in practice, we do not know the values of statistics from all possible samples. So we cannot calculate the exact confidence coefficients for a procedure as done in example 2.7. And yeah, now let's move to calculating confidence interval for large sample. And in introductory statistics class, we rely largely on asymptotic as the sample size goes to infinity results to construct confidence intervals for an unknown mean score. So now it is also mentioned in many introductory statistics book that a sample size or the magic number of sample size equal to 30 is sufficient enough. Is sufficiently large enough to say that our sample is large, but um, many population that have been sampled by using the sample size equal to 30 are proven to be highly skewed. So in this case, you may need to make sure that you have to check everything. You have to check the distribution of the mean to make sure that you can use the central limit theorem, right? So now, let's say if your sample is large, now you can use this formula to calculate the confidence interval. Okay, you can use the y bar minus z alpha over 2. This one you have to refer to the table, okay, to the table in which you have to also determine the alpha value, and usually the alpha value is equal to 0.05. Okay, and you must also calculate the standard error of y bar, in which you can use this formula to calculate the standard error of y bar. And if you are going to calculate the confidence interval of y or the mean score, make sure that you use the standard error of the mean score at the back here. Okay, and if you, let's say you would like to conduct or to calculate the confidence interval again, but this time for the population total, what you have to do is you have to use this formula. Oops, sorry. T minus z alpha over 2 times standard error of t hat. Okay, same goes to this one, t hat plus z alpha over 2 times the standard error of t hat. And how to get the standard error of t hat? It is equal to n times the standard error of y bar, that is this value. All right, so it is also equal to n times 1 minus sample size over population size times standard deviation over square root of n. So this is the confidence interval for for the t hat if you have large sample. And let's say if you have maybe unknown variance or unknown standard deviation, so in this case you have to use the t, okay, the t alpha over 2. This one you have to refer to the um, table, that is t distribution table. The previous one is z distribution table, okay, and you have to determine the degree of freedom that is equal to n minus 1. In this case, this is the degree of freedom, right? And the t alpha over 2, in which usually the alpha used is also 0.05. But in research or in survey research, it is up to the researcher. uh, uh, it is up to the researcher whether you want to use alpha 0.05 or alpha 0.01, alpha 0.0, alpha 0.1, and so on. It is up to the researchers, depends on the type of the research. You may and can use a bigger alpha value if your research tend to be like a perception kind of research, because the data tend to change over time, right? So yeah, I think that's all for confidence interval, and see you again when we will discuss about the sample size estimation. Thank you.